All right, so what we're going to do here is we're going to look at some uses of our number set. The book takes what I think is a little aside and looks at sequences. And so a sequence is a series of numbers, and there's actually a famous number series. This is the Fibonacci sequence. I said series, sequence. Series is when I add up the total of all these things. Fibonacci sequence. And what we do is we will give a letter with a subscript to identify the first number, the second number, the third number, and so on. In fact, we can take it up to some nth number, some way of talking about however many numbers we can take in our sequence. And so what we can do then is have a way of talking about that. So if we look at this sequence, the third number, whoops, I missed one in there. Bad, Jeff. There we go. Famous sequence, and I forgot one of the important numbers. There we go, that's better. So the third number is 2. And so, in fact, I'll do it this way. A sub 1 is 1, A sub 2 is 1, A sub 3 is 2, A sub 4 is 3, A sub 5 is 5, A sub 6 is 8, A sub 7 is 13, A sub 8 is 21, A sub n, what is A sub n? And, well, we can look. These first two numbers in this particular sequence are anchors. And then A sub 3 is equal to A sub 2 plus A sub 1. A sub 4 is equal to A sub 3 plus A sub 2. A sub 5 is A sub 4 plus A sub 3. And so notice each number in the sequence is the addition of the previous 2. And the sequence is actually used for things that grow a lot. The Fibonacci sequence appears in many different things in nature. And so sequences can be very useful ways of representing a pattern that we see in nature. The Fibonacci sequence, the actual answer for A sub n, is actually very difficult to calculate. I'm trying to see if did I spell Fibonacci right? But it has a really unique pattern, and this is something that I derive in one of my linear algebra classes for students. Oops. And what's really neat about the Fibonacci sequence is it has square roots in it. It has irrational numbers. Square root of 5 over 2 to the nth minus 1 minus square root of 5 over 2 to the nth. And so this is a very weird number set that all of these things are integers, but it takes irrational numbers to figure out the nth term. And I had one of my students in a previous place write a computer program to generate these, and he did them by hand, where the computer would do this addition, and then he had the computer do it this way to see how he could make it faster. And this is a fairly famous sequence. We're not going to look at this type of answers for nth terms, but what happens with a lot of sequences is the pattern and the creation rule for the pattern over here can sometimes be simplified. And so that's what we're going to do, is we're going to look at sequences for patterns. And so the first type of sequence we're going to look at is a simpler introduction than the Fibonacci's, and it's called an arithmetic sequence. I'm going to change the whites bugging me now. You're going to see me switch colors often, as I think my eyes get tired of one color after. And what happens in an arithmetic sequence is that there's a common difference in terms. So for example, the book is going to use, try to get my numbers right here. And so on and so on, and the sequence can continue onwards. And if I look at any two terms in here, 146 minus 142 is 4. 150 minus 146 is 4. And so the common difference in this sequence is 4. Which means that I know the next term is going to be 162, and so on. And I actually have a way of generating multiple terms. In fact, I start with 142, right? And I add to it 4 times n minus 1, right? If this is the first term for n, and this is the second term. But I might be able to do some of this better. There might be some better things I can do in this. Because notice what happens here. We can factor things out, right? And so I can say the nth term of my sequence is found by this little formulae. Well, that's what we're going to do, is we're going to look at patterns and see how we can pull patterns out. If one of the things is predicting numbers, then in sequences are a series of patterns that we can do to help us find that pattern and predict that pattern. And so in general, an arithmetic sequence is a sub 1 plus n minus 1 times the common difference. Right? If we let d be the common difference, which is what I did here. Right? I did a sub 1 plus n minus 1 times the common difference. So what we can do is we can find a common difference or write a common difference. So let's say I want to find the 8th term of a sequence whose first term, a sub 1, is equal to 4, and the common difference is negative 7. So this is a decreasing sequence. And so I can go, hey, I want to find n equals 8 out of the formula that a sub n is equal to 4 plus n minus 1 times negative 7. And I'll rearrange terms here, 4 minus 7, n minus 1. And I want to find the 8th term, so that's 4 minus 7 times 7, or 4 minus 49, or negative 45. And that would be the 8th term in the sequence. I don't have to create each piece in it. The common difference allows me to skip steps. There's another type of sequence, which we're going to call geometric. And what happens is, it happens because there is a common ratio between terms. There's some multiplier. So we multiply by a common ratio between terms. So for example, here's a sequence where if I take the first two terms and I take a sub 2 and divide it by a sub 1, I get 5. If I take a sub 3 and divide it by a sub 2, which is 25 over 5, I get 5. If I take a sub 4 and divide it by a sub 3, I get 5. And so the ratio is 5. And so geometric sequences use multiplication. And so we can write a geometric sequence. Let's take a geometric sequence starting at 6. So we'll start at 6 and we'll have a ratio of 1/3. So we start at 6, and so the next we're multiplying by 1/3, so we get 2 and 2/3. Then in 2/9, right? Because multiplying by a third, and 2/27, multiply by a third, 2/81, and so on and so on and so on. I take this term, I multiply it by a third. I take this term, I multiply it by a third, and we get this creation rule that builds our pattern. Geometric sequences actually appear quite often. In statistics, we'll learn about a geometric series which comes about because of geometric sequences. And we can find a nth term by using the formula that a sub n equals a sub 1 times r to the power of n minus 1. And so we're using the idea that multiple multiplications, we use powers. Right? In the addition rule, for the additive series, or additive sequence, we use the idea that multiple additions are a multiplication. And we go to n minus 1 to find the nth term. So we're following kind of the order of operations and how multiple multiplications are powers, and up above, multiple additions are multiplications. Our nomenclature works for us in building these patterns. And so let's find the 8th term of a geometric sequence. So we'll find the 8th term starting at, let's see, -4 with a ratio of -2. And so a sub n equals -4, -2 to the n minus 1, or 8 minus 1, I guess, which is -4 times -2 to the 7th. Ooh, this is going to be a lot of multiplication for me, but the first thing I'm going to do is realize that this has to be negative because it's to an odd power. So I'm just going to pull the negative sign out front, and then I'm going to say 2 to the 7th. Because that's going to let me do is realize my answer is going to be positive. And I'm going to have 4 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7. All right, so let's see. What is 2 to the 7th? I always said 2 to the 0 is 1, 2 to the 2 is 4, 2 to the 3, whoops, 2 to the 1, there's 2 in there. 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, and 2 to the 7th is 128. And so all of that becomes 128. Of course, hopefully for you, you're running to your calculator, right? Mine's on that other screen there, and I didn't want to turn off the screen. And now 4 times 8 is 2. Carry my 3, it's 1. Carry my 1, 5. And so the answer is 512. A thing to notice is when our r's are negative, this should alternate in signs. And that's a thing that we're going to call alternating sequences. And we can get the sign alternating coming out of it. All right, so that's sequences. I hope you play with some of those on the homework, and they can show you ways of creating pattern, which again, pattern and prediction is the goal of mathematics. So exploring patterns and looking for the art and the kind of I want to say the subtleties that come out of patterns. I mean, there are a lot of these geometric sequences and other sequences we can visualize with graphs. And I'll see if I can add some graphs online so you can see what these look like. All right, until again.